Hello, everyone. We're gonna continue on talking about statistical inference, and so far we described what statistical inference is, and then we talked about the estimation of distribution parameters, population parameters for a single value, so estimating the mean, or the variance of a normal distribution, estimating the theta and omega squared parameters of the log normal, etc. And that we called point estimation. But then also we talked about interval estimation with confidence intervals on the mean, confidence intervals on the mean with unknown variance, confidence intervals on the proportion or the variance itself. But there's another type of problem that is encountered pretty often with statistics, and that's when we have to decide which of two competing statements about a parameter value is true or not, or rather, which one we think that we can support with the data, and which one we do not think we can support with them. So, for example, if we were interested in the yield strength of rebars that satisfy a minimum threshold, the way we would approach it is we would try to take samples, we would try to calculate the mean yield strength, and then we would ask ourselves, what is the confidence level that we have that the mean that we calculated from the sample translates to the population mean, and is that population mean greater than a threshold? Because the idea is that, we take the samples, but we don't care about our sample mean being greater than the threshold. We care about inferring whether the population mean is going to be greater than that threshold. So this is similar to deriving the confidence intervals, but it's posed in a different way, where, again, we can try to answer the question of which of two competing statements is supported by data and which isn't. And that's what's called hypothesis testing. And hypothesis testing essentially revolves around a statistical hypothesis that we make about the parameters of one or more populations. And we would need, of course, two hypotheses to make this interesting and test them out. And they're going to be competing. And as I mentioned, this approach, or the things we're going to talk about today, are very similar to what we talked about in confidence intervals. So there are two hypotheses that we're working with. The first one is called the null hypothesis. The null hypothesis is H naught, and for example, when we're dealing with the mean as the parameter of the population, the hypothesis is expressed as the true mean being equal to a certain value, mean mu naught. And then we also have the alternative hypothesis, which is notated as H1. And if we again take the example of means, then that says that the true mean is not equal to that value that we're hypothesizing. In practice, what the null hypothesis is depends on the person setting up the problem, so you. But most of the time, the null hypothesis, you can think of it, again very crudely, but you can think of it as the status quo, what's sort of expected for a process or a variable of interest, and again, with respect to their parameters. So the idea is that we need to have a data set from our sample that essentially will support something that is contradicts the status quo. So if we're gonna find something that's of interest, then we would go against what most people believe, which would have been the null hypothesis. So we're trying to essentially reject the null hypothesis and support the alternative hypothesis. So again, very crudely, that's how you choose what the null hypothesis would be. But we do have the freedom to essentially set the hypothesis any way we want, but that will change how the calculations are done. And most of the time, the null hypothesis is an equality claim, unless the alternative hypothesis is not an inequality, but it's greater than or less than a certain threshold. And we've talked about this in terms of, for example, the upper bounds or lower bounds. So sometimes in engineering especially, we care about minimum or maximum values. So then the alternative hypothesis would be formulated along inequalities like that, or greater than or less than. And if that's the case, even though we might express in notation at least the null hypothesis as mu equals to a value, if the alternative hypothesis, for example, is mu less than mu naught, then the null hypothesis will become, so for example, let me write this out here actually. So for example, if our h1 was mu less than mu naught, then the null hypothesis, although we write it like this, it implies this. And as an example that we're gonna bring up again later in this lecture, let's talk about the burn rate of a propellant. Let's say that we have a null hypothesis of our mean being equal to 50 centimeters per second. The alternative hypothesis would be that the mean is actually not equal to 50 centimeters per second. And if we take a sample of 10 observations, so 10 specimens, what we'll end up with is these essentially two regions but they look like three here. But if we assume that, hey, a null hypothesis, the true mean is equal to 50, we take our sample, and depending on the alpha level, so you remember how in confidence intervals we would look at 95%, we'll do the same thing here where we will use the sample mean to essentially come up with these z critical values here. So what these critical bound will do is it will set this region of failing to reject the null hypothesis here. So if our statistic actually falls inside this region, we're going to fail to reject the null hypothesis. So we can't really say whether the mean is actually not equal to 50. However, if our statistic falls in this area here, that corresponds to a sample mean of greater than 51.5 or less than 48.5, then we would be able to say, you know what, actually it looks like the true mean is not equal to 50, but it's somewhere in here. So we would reject the null hypothesis. Same thing on this region as well, which brings us to the definition of the acceptance region and the critical region. And let's go back here. You can probably guess that this is the acceptance region, and these are the critical regions. And the two bounds there that are coming from, in the case of the mean, they would be the mean values of 51.5, 48.5. Those are the critical values. So if the values fall inside the critical region, we can reject the null hypothesis. And by rejecting the null hypothesis, there is a probability that we made a mistake, that actually, despite the fact that we rejected the null hypothesis, we weren't supposed to. The mean is actually closer to 50. So when the null hypothesis is actually true and we reject it, then we have what is called a type 1 error. Whereas a type 2 error would happen if we do not reject the null hypothesis, when in fact we should have. So when the null hypothesis is actually false and we fail to reject it, so we're still within the acceptance region, and that's a type 2 error. And this is just a summary. So if the null hypothesis is true, and we fail to reject the null hypothesis, so that's no error, that's exactly what should have happened. But if H naught is true, so the null hypothesis is true, but then we reject it, that's a type 1 error. The type 2 error comes when we do not reject H naught when we were supposed to. Now, if we think about the probability of a type 1 error, that is the probability of rejecting the null hypothesis when H naught is true. And that will be the alpha level. And this is very similar again to confidence intervals. But we have to reformulate what goes in here in that probability. So the probability of alpha in this case is called the significance level, or the size of the test. So as we mentioned last week, we were talking about statistical significance, and this is exactly the definition of it. The statistical significance corresponds to the probability of a type 1 error, or the probability of rejecting the null hypothesis when the null hypothesis is actually true. So we want to keep this as small as possible, of course, right? So if we, for example, we were talking about a 99% significance, and sometimes we use that interchangeably. 99% or 1% would be the alpha, but the smaller this probability is, the better for us, because we would have less of a chance to rejecting the null hypothesis when it actually is true. So going back to our example of the with the propellant, and we have the mean here of 50. That's the true mean. So then if we have those critical values being here at 48.5, 51.5, then the areas where we would be in the critical region, we would be in these shaded areas here. And what we can do is we can calculate the probability that corresponds to this value of x, which we would transform to z, and then from the z we would find the from the lookup table we find the probability on the left tail and the right tail, add the probabilities together, and we get that significance level alpha. Now, the way to reduce alpha, because that's our goal as we've seen, there's a couple of ways to do it. One would be to change those critical values. So we would have to push them to the right and left here, so outwards, because then that would reduce the area, right? The shaded area that's outside of those bounds. So that's one way to do it, but that way, as we've seen in confidence intervals, we increase the confidence interval itself, so we reduce the alpha. So same thing here, where we would change the critical values, so then we would reduce the alpha for the hypothesis test. And another way of doing this is, again, similar to the confidence intervals, we can increase the sample size. So when we increase the sample size, we will reduce the alpha level for if the critical bounds remain constant. With alpha being the probability of a type 1 error, we have the equivalent concept of type 2 error. That's not alpha anymore, it's beta. So beta is the probability of a type 2 error, which, remember, is the probability of failing to reject a null hypothesis when it actually is false. So despite the fact that H naught is false, we failed to reject it, which we should have done. And the probability of a type 2 error will increase pretty quickly when the true value of mu is actually very close to the hypothesized value. So going back to our previous example, if we have a hypothesized value of 50.5 and the true value is 50, then the probability of a type 2 error of again failing to reject a null hypothesis when it actually is false increases pretty quickly. And we can see this in these two figures here. So if we start out with the left figure here, you'll see that we have the null hypothesis, which is a mu of 50. And then we have the alternative hypothesis, which is that mu is equal to 52. Now you see that 52, what we're looking for, the type 2 error, is the probability of failing to reject H naught when it actually is not true. So we would be here in this shaded area for that probability, right? Because we have the probability here that here the probability here would be, again, remember, this is the critical region here. So the probability for the alternative hypothesis here would be from this point to this point here. So you see that the probability is this one. However, if the alternative hypothesis is actually very close to the true mean, so if it's very close to between like 50 and 50.5, for instance, then we see that this shaded area is actually increasing quite a bit, and that's the type 2 error. So beta will be high very quickly depending on how we hypothesize about the mean value relative to the true mean value. Now there is, remember, if we increase the probability of type 2 error, then we have more chances to reject to fail the null hypothesis when it actually is not true. However, if the null hypothesis is not true, which means that the mean is actually 50.5 instead of 50, then when we think about it in terms of practical, like in terms of engineering, in practical sense, does it matter that much? We have 50.5 versus 50. Well, we're close enough, right? But despite that, we still will reject, will fail to reject the null hypothesis. So the probability of type 2 error increases. So just to summarize here, and again, we've only touched upon some of these topics, but with the hypothesis testing, if we have the acceptance region being between 48.5 and 51.5, and we have a constant sample size of 10, the alpha here, the probability of rejecting the null hypothesis when it's true, is 0.05. But now, however, you see that if we have the type 2 error, when mu is 52, we would have 0.2643 as the probability of a type 2 error, which dramatically increases when we have the mu being very close to the hypothesized value, so 50.5. Similarly to this, we see that the probability of the type 2 error also increases dramatically from 0.5 to 0.9705. And again, this assumes that we are keeping the sample size the same. So now you see that the bounds of the critical values of the acceptance region got larger, and by them getting larger, we see that the alpha actually was reduced. But that doesn't really do anything for the other feature of the type 2 error that increases dramatically depending on how close the true mean and the hypothesized mean are. And we can see a similar story here, but if we increase the sample size. So by increasing the sample size, we can get some reductions, but that also has to go along with having the same critical values, which in this case we don't. Now The type 1 and 2 errors are related because the reducing the probability of one type of error will always lead to the increase in the probability of the other. If we keep the sample size the same, obviously if we decrease the probability of, let's say, type 1 error, so we decrease the probability that we're gonna fail the null hypothesis even though it's true, so that will change the type 2 error in the opposite way. So again, if we have a type 1 error that is let's say 0.05, 0.95, and then if that gets decreased, then we should be seeing an increase on the type 2 error, which is the error of actually rejecting the null hypothesis, well, not rejecting the null hypothesis despite the fact that it's false. And the sample size actually increasing will reduce the type 2 error, and we saw that the increase will also reduce the type 1 error. And when the null hypothesis is false, the type 2 error will increase as the true value of the parameter approaches the hypothesized value, as we've shown in the previous plots. So we've talked about, what is a hypothesis test. We've talked about the type 1 error and the type 2 error and the probabilities. The type 1 error probability is actually the significance level, and then the type 2 error will be related or connected very tightly with the type 1 error. Another concept that's very important for hypothesis testing is the power of a test. And the power of a test is essentially the probability of rejecting the null hypothesis when the alternative hypothesis is true, which is what we wanted, right? So if the alternative hypothesis is true, we want to be able to reject the null hypothesis. But sometimes there's, the data just don't support it. So if we reject the null hypothesis, it doesn't mean that the null hypothesis is true. It means that we just don't have adequate data to actually prove this. The power is computed as 1 minus the probability of a type 2 error. And if the power of the test is considered too low by the engineer, then we can either increase A or N. After the power of each hypothesis test, you might have heard this term, the p-value of a hypothesis test. And the p-value is corresponds rather to a fixed significance level. And the way it corresponds to that is that's the first thing we do, right? So we just saw that we can test the null hypothesis or the alternative hypothesis, and we say, oh, I want to look at it at the 95% level, the 99% level. On the other hand, that approach can be limited as if I decide that, I want to test this hypothesis at the 95% level. For somebody who's more risk averse or less risk averse, because the significance level that we choose actually corresponds to the risk of not estimating the parameter correctly. So for a lower significance level, we would get a different value. For a higher significance level, we would get a different value, and consequently we would be able to reject or not reject the hypothesis. And this is the type of problem that p-values are trying to solve to a degree. Because with p-values, we don't have to specify an a priori significance level. What we find is what is the smallest level of significance that would actually lead us to reject the null hypothesis with a given data. And if we decide to look at an example here where we have the null hypothesis having a mean of 50, whereas the alternative hypothesis having the mean being less than or equal to 50. And if we had a sample size of 16, we know the variance or the standard deviation of the distribution at 2.5, and then we have a sample mean of 51.3. So the p-value, again, is the value, the smallest value that will allow us to reject a null hypothesis. So again, following the example here with the mean equals to 50, we can get the critical values at 48.7 and 51.3. By performing the z-transform, we end up with the probability of z being between minus 2.08 and 2.08. So we end up with a p-value of 0.038. And again, if we look at the definition, it's the smallest value that would lead us to the rejection of the null hypothesis with the given data. So the p-value basically tells us that 4% is the significance level that would allow you to reject the null hypothesis. And one thing to take note is that p-values are actually random variables themselves. So in these plots here, we used, or at least the authors of the textbook used, a computer simulation to generate a number of p-values. So you see the p-values here are between 0 and 1, as we would have expected from the definition of p-values. And what we see is that the shape is fairly uniform, so and relatively flat, but the distribution is uniform. Now, if we look at putting the mean equal to 1, that changes the picture dramatically. So you see here that the p-values are actually very close to 0. So the probability, again remember, it's the smallest value that would lead to rejection of the null hypothesis. Oops. So you see here that the smallest value, we get most of the values being less than 5%. So the probability that we would reject the null hypothesis, if, remember, mu equals 0 is true. So if we say, oh, well, what if mu equals 1? Well, then the probability of actually rejecting the null hypothesis increases quite a bit. So that's the smallest p that we need to show that we can reject the null hypothesis. And the same thing here would happen, where you would get even more of those p-values located near the 0 area here. So, having covered these concepts of what is a hypothesis test, what are the critical values, the acceptance region, the critical region, and what is the power of a test, and what is a p-value, these are the concepts that we need to know in order to proceed with solving some problems. But the general procedure for performing a hypothesis test includes the following steps. Well, first we have to figure out what parameter we're interested in. So most of the time it's the mean of the population, but as you've seen, there's others. And then what we need to do is state the null hypothesis, state the alternative hypothesis, and then depending on the type of data we have, the sample, the distribution, then we can decide what is our distribution going to be for the type of problem. And that will tell us then, the type of problem will tell us whether we need to use a distribution for the test statistic that's different than the normal distribution. So after we calculate the test statistic, or at least determine it, or which one it is, then we need to essentially say, well, this is how we're going to reject a null hypothesis if it comes to that. What we would do is we would say, oh, I need this x and y and z to reject h naught. And usually what that translates to is, saying, well, I want to look at the 95% level So that gives us the z value that is critical, and then that really has a very straightforward approach to rejecting the null hypothesis and performing the computations. And finally, we can draw conclusions. We can decide whether the null hypothesis can be rejected or not. And this brings us to a different topic of statistical versus practical significance. And this here table just shows us the p-value and the power of a hypothesis test for different sample sizes. So we can see here that for a sample size of 10, we've got a p-value of 0.527. And that value corresponds to the power of a test, again when the truth is 50.5, of about 10% probability. But that's the power. So that that power is pretty low. So if we increase the sample size, let's say we go to 100 specimens or objects, so sample size of 100, then we see that the p-value, so again the probability, the smallest significance level where we can reject a null hypothesis, that becomes much smaller than what we had with 10 samples. Becomes 0.046, and if we go even down, if we're further down, then we see that we're getting some extremely low numbers. But what that does, and you can see here hopefully the relationship between all those different concepts that we just talked about in this lecture, is that when the power of the test changes, when that p-value changes, and with that we're going to stop here, and on Thursday we're going to start working on some problems that hopefully will answer a lot of the questions that I'm sure you have, and also will make things more well, at least make you be able to see how you can use these to solve the problems that we're going to have in the final or in the homework.